Okay, this video tutorial looks at the mathematical strand of linear and non-linear relationships, and more specifically we're going to focus our understanding on growth and decay. So when we're looking at growth and decay, we can use exponential functions to determine the growth or the decay of a variable. Okay, so this is when the factors are either increasing or decreasing exponentially. Alright, so if we look at the equation that we've got here of f of x is equal to k times a to the power of n. In this particular case, if a is greater than 1, then we're going to have an exponential growth. Whereas if a is greater than 0 but less than 1, we're actually going to have an exponential decay. So let's have a look at an example question. It says here, under favourable conditions, a population of rabbits will grow exponentially. So suppose the population is initially 100 rabbits. The population doubles every month. Okay, so this gives us the equation of the population equaling 100 times by 2 to the power of t, where t represents the amount of months for the exponential function. So we can use the above information to determine the following questions. So how large the rabbit population will be after 3 months. We simply just put 3 in as our t, so 100 times 2 to the power of 3, because now 3 is our t. This becomes 100 times by 8, so therefore the population is going to be 800. We can also do it again if after 8 months we use the same population of 100 times 2 to the power of 8. This becomes 100 times by 256, and this becomes 100 times 256, which becomes 25,600 rabbits. Okay, so here are some practice questions I'd like you to have a go at that are very similar to our example questions that we went through. Please feel free to pause the video, have a look at the questions. When you think you've got the answers, continue the video and we'll see how you went. Okay, our first question says, during a locust plague, the area of land eaten n number of weeks after the initial observation, so n representing the number of weeks after the initial observation, is given by a formula. The area equals 8,000 times 1.4 to the power of n hectares. So A is find the initial area. Well, the initial area is where n equals 0. So we know that n equals 0 because it was the initial time. So therefore A equals 8,000 times 1.4 to the power of 0. Now anything to the power of 0 is 1. So this is simply 8,000 times by 1, which is just 8,000 hectares. And B, it says find the size of the area eaten after 4 weeks. Well, we put that into our equation. A equals 8,000 times 1.4 to the power of 4. A, if we put that into our calculator, is going to be 30,732.8 hectares. And we can also do it after 7 weeks. So we can essentially go, our area is equal to 8,000 times by 1.4 to the power of 7. Our area, therefore, is going to be 84,330.8 hectares. Now we can do something similar. Obviously, they are growth examples, but we can do something similar for decay examples. And it says here, the current I flowing through the electric circuit of a fan t milliseconds after it's switched off is given by the formula of I equals 320 times 0.7 to the power of t milliamps. Find the initial current. So again, the initial current is when t equals 0, So therefore our I equals 320 times 0.7 to the power of 0, which is therefore just going to equal 320 milliamps. If we're going to look at B, we've got I, and this is going to be 4 milliseconds, so that is I equals 320 times 0.7 to the power of 4. We can put that in our calculator. And that's going to be 76.83 milliamps. And we can now do our 10 milliseconds, which is I equals 320 times 0.7 to the power of 10. And we can put that into our calculator as well. And we'll end up with basically 9.04 milliamps.